All right, we'll go ahead and get started then. So just like the morning review session, we just have basically a bunch of practice problems to go over to try to help you prepare for the final exam. Um, so I have the entire practice final exam and all 12 of those questions that we can go through. And then I also selected a few more extra problems that we can also go over as well that you all haven't seen before. But this is all really your time. So I'll just kind of let you guys lead it with what questions you have and where. So I guess first off, does anyone have any questions over the practice final and any of the problems there? You can just type whatever question or whatever the question number is in chat for the practice final. So no one has any questions over
Yeah, I
the
don't have any
practice
like
final?
specific questions, but I wouldn't mind like going through it for sure.
Okay. Yeah, sure. Yeah, we can just start from the top then and kind of walk through it. So here's problem one. So we're supposed to indicate whether each of the following statements are just true or false. So let's go ahead and we can just kind of go through it together, and we can stop if there's questions anywhere. So let's go to the part A. So the empty set is a member of every power set. Do we think that's always true or false? You just type in.
True.
Yeah, this is always true. Because remember that the power set, right, is the set of all subsets. And the empty set is a subset of every set. So the power set, by definition, will include the empty set. And then
Did you say that again? The power set is the what, and the subset is the what?
The power set is the set of all subsets. So, for example, like I'll just write over here, if I was looking at like the power set of, let's say the set 1, 2, 3, right? The power set is it's a set, and it's a set of all subsets. So the empty set's a subset of the set 1, 2, 3, the set 1, 2, and 3. Those are all subsets. And then we can do pairwise. And that's all subset. And then, of course, the set itself is a subset. And so then this is what we'd have for the power set. It's just the set of all the subsets. Does that clear that up?
Yeah, and so the empty set is just an empty set of one of those sets.
Yeah, the empty set is an element. Yeah, it's an element of the power set because the empty set is always a subset of any set.
Okay.
Awesome. Yeah, good questions. Yeah, just whenever you have a question, just feel free just to unmute yourself and ask away. So if you go to part B, right, we're looking at for all n in this set, -1, 0, 1. Does n divide n squared? Or in other words, if we use the definition, right, that this means that n divides n squared. In other words, this is equivalent to meaning that n squared is equal to some n times k, where k is an integer.
Can you divide by 0?
No. Can't divide by 0. Or in other words, Yeah, because I think what you were hoping to say there is that this is n squared over n is equal to like k or something. But n could be 0, so that doesn't work.
So it's false because there's one counterexample.
Yeah, what's the counterexample you see?
The 0, right?
So you're saying like that 0 equals 0 times k is not true?
Yeah, because 0 can't divide 0.
Well, this is okay, right? Because this is, we're not doing any division here. This is just multiplication. Right, because if n divides n squared, that just means that n squared is a multiple of n by some integer, right?
Is -1 the counterexample?
Yeah, and this is z, not the integer z. This is z plus, so all the positive integers, and yeah, -1's the counterexample. Because if you take -1 squared, right, that's equal to 1, and you want to find some integer k, some positive integer k, where 1 equals -1 times itself, and that doesn't work, right? This requires that k is negative. And that doesn't follow the definition of divisibility, which requires k to be a positive integer. So this is false. And just because of the -1 counterexample. And then there's a similar question. So for part C, we're asked a similar thing, if there exists an n in this set where 2 divides n squared. So in other words, does there exist an n where n squared is equal to 2 times k for some k that's a positive integer?
I'd say no.
So you're saying no here. Why do we think maybe no? Or what's your thought process here?
If we plugged in like 1 to n squared and then divided that by 2, it wouldn't be an integer because it'd be a fraction.
Yeah. But is that true for all of the n? Like, because this is there exists. So does that happen?
Would 0 work? Is 0 an integer?
Yeah, zero's an integer. So are you saying like for n that, in other words, does like 2 divide 0? Is kind of the thought process here.
Yeah.
And yeah, that works out. One sec. I messed. Yeah. Yeah, one sec. Yeah. Yeah, you are right. Yeah, because scratch what I said. I don't know why I added the positive earlier. I was like doubting myself, I think, on why this was false, but yeah, divisibility just means that there's any integer. And I actually think that the B is yeah, because C works and solely because of zero working, because does 2 divide 0 squared? Well, yes, it does, because 0 squared is equal to 2 times 0, and 0 is an integer. So where did my stuff go?
Hey, also, class, the random question is the real final exam just going to have 12 questions, just like the practice?
It may have more or less. We can let you know. We'll post an announcement for that. We haven't finished finalizing it yet, because we go through several drafts of the exam. Like first we write an exam that we think is fair, and then all of the TAs we try it a couple times to see if we can do it in a reasonable amount of time, and we're not done with that yet. We're still kind of trying to figure that out. So when we're done with that, we'll post an announcement
Okay.
to let you know. But I just want to, yeah, let me just, yeah, okay. So then if we go to D, does every function f from its set to itself, is that onto for every set A? So if we're looking at a function just from the set to itself, is every possible function onto if that's the case?
What's the definition of onto again?
So recall that onto says that for every element in your codomain, there's some element from the domain that maps to it.
True.
True. In this case, it's not necessarily true. For every possible function. And why is that? Well, because we can define a lot of functions that are not onto in this case. Like for example, we can take a function that maps like the naturals to the naturals, but takes every number and maps it to an even integer, and that won't be onto. You'll miss something.
So this was for like every single possible rule.
Yeah, this is saying for every single function, and that's the issue here. Is because we're talking about all such functions. This doesn't work. Otherwise, it'd be really easy to prove. Onto is a function is onto. You just have to check if the sets is itself, and it's unfortunately more involved because we could take a function like f of x is equal to like 2x, and we could go from the integers to the integers, but you're not going to map anything to, for example, 1, and the integers won't be mapped onto. But this is a valid function. So.
So then what does A to A mean then?
Oh, that just means the set you're mapping on. So for this example, I said we were going from the set Z, or the integers, to the integers. So this is your input, and then this is your output.
But then how are you able to do that example where it was the natural numbers into the even natural numbers? Isn't that not considered A into A?
Yeah, no, so that's what that's this function, f of x equals 2 to x. It's mapping everything to an it's mapping everything into here, into some even value in here. And that's why it's not onto, because nothing is going to map to like 1, for example. 1 is not mapped onto by this function, because for 1 to be mapped onto by something, by an integer in x, that would mean that that value would have to be a half, and that's not. It's coming from the integers.
Okay, I think I understand now.
Yeah. Yeah, so you just have to be careful. Especially when we're given for every function. If that's the case. Any other questions on that? So then if we go to E, for every set A, there exists a function that is 1 to 1. So do you think that's the case? So remember, when we're talking about for every set, right, you always have to think about, are we looking like, think about like finite sets as well as infinite sets, like the integers, and whether or not there is always a function that is 1 to 1.
True.
Yeah, what would the function be if it is true? So we can always take like the function here that always works is the identity function. So it's the function f of x that equals x. It takes every input and it maps it to itself. And that'll always work for any of the sets. And then if we go to F, what do we think here? So is the cardinality of a set S always less than or equal to the cardinality of the cross product of its set for every set S?
True.
True. Yeah. So what is the cardinality of the cross product of a set?
Is it times 2 or squared?
Yeah, it's squared. So the cardinality of S cross S, that's just equal to the cardinality of S times the cardinality of S, right? Because when you're doing the cross product, you're creating all such pairings. So if you've got like the set 1, 2, 3, and the other set like 1, 2, 3, you're going to come up with every such possible pairing. So you're going to match 1 to 1, 1 to 2, 1 to 3, 2 to 1, 2 to 2, 2 to 3, 3 to 1, 3 to 2, 3 to 3. And that'll be a squaring process. And so in this case, right, so then the equality we're given is it always true then that the cardinality of S is less than or equal to the cardinality of S squared? And yeah, that always holds for every set. What about if we extend that to this idea to kind of like the power set? So is the power set of the power set of S less than or equal to the power set of the cross product?
I'd say false.
Okay, so so why would we say false? what is the cardinality of a power set? So, right, remember that the cardinality of a power set is 2 to the cardinality of the set. So when you're asked problems like this on the exam, like it's true or false, don't just necessarily go with the, like, I think it may be this, but try to remember, like, because true or false questions are a way for us to test like whether or not you know like these definitions, right? Like, do you, because this is really a question, do you know how to find the cardinality of the power set and the cross product is what we're looking at here. And so if we use the substitution here, what we're really asking here is 2 to the cardinality of S. Is that less than or equal to 2 to the S squared?
I think the left side is bigger.
Yeah, because we can simplify this, because this is also equivalent to just asking us 2 to the power set of S less than or equal to S squared. And this will end up out to be false. And like for one example, just plug in 1. So if you have a set that's size 1, right? 2 to the first less than or equal to 1 squared. And 2 is not less than or equal to 1. So that doesn't hold. And in general, once you have a large enough size for your set, this won't hold. And you can do an induction proof. And you can prove that like 2 to the n is always, or 2 to the n is less than n squared when n is greater than or equal to 4, I think. And then, so let's go to, so H, so we've got a logic question here. So is X or not X? Is that always true or always false for any Boolean X?
True.
Yeah. Yeah, this is always true. And you can plug in a couple examples if you want for true and false, and you'll see that one of these will always be false, right? Because you're either looking at X or not X, and no matter what Boolean function, one of those will be true, and anything ORed with true is also true. So what about if we change the OR to an and? Is X and not X? Is that always true or always false?
False.
False.
Yeah, it's always false. One of these values will always be false, and anything ANDed with false is false. And then what about the last one? So if A divides B plus C, that means that A divides B or A divides C.
False, because if A was 2 and B and C were 1, A would divide B plus C, but A would not divide B, or A would not divide C.
Yeah, that's a perfect example. 2 divides 2, but 2 does not divide 1. Yeah, and there's lots of these that you can come up with for why that doesn't work. So are there any other questions on these true or false ones?
Why was E true?
E is so E is true because the function we can find is the identity function, is the function that works from any set to itself. And so the identity function just takes its input and it maps it to the same, like the output is just whatever the input was. And we just call it the identity function. And that'll be a one-to-one function for any set. Also always an onto function.
Okay, thank you.
Yeah, so any other questions here? Cool. Let's go then to problem 2. So we've got a problem on expectation. So we're at a company that plans to invest in this project, and there's a 40% chance that we're going to lose $2,000, a 40% chance that we'll break even, so we won't lose or gain anything, and a 20% chance that we will make $5,000. And so we're asked, should we proceed on the project? In other words, will we make money on this project based on these odds? Right, and then if we can make money, we'll say, yeah, let's go ahead with the project. So to start this, right, we're going to look at the expectation, and right, in general, the expectation for this value x, where x is the amount of money that we plan to make, right? How do we calculate expectation? Well, it's just the probability times whatever the value is, right? So it's the probability of x times whatever we plan to earn. So there's a 40% chance, so there's a 0.4% probability that we're going to lose $2,000. Right, so we take 0.4 and we multiply that by what will the negative $2,000. And then there's a 0.4% chance that we don't lose or don't earn anything. So 0.4 times 0, that'll just be 0. And then there's a 20% probability that will earn $5,000. Right, and so then if we sum all these together, right, 0.4 of 2,000 is just 800. That'll be 0, negative 800, excuse me. And then that'll be plus 1,000. And so this will be a positive $200. Right, so we should proceed. So are there any questions here? No questions? Awesome. Okay, so let's do the third problem. So here we've got a counting problem. And so we're dealing out poker hands. So just 5 cards. And we've got a standard deck of 52 cards. And so we want to find the number of ways that the player could be dealt a spade flush. Basically, what's the number of ways that the player could be dealt 5 spades? So we've got a counting problem, right? We want to count the number of ways that this can happen. So if we're doing a counting problem, we first want to figure out a couple things, right? Does repetitions matter? And does order matter? So does repetitions matter for this problem? Do we allow repetitions or not?
No.
Yeah, no, we can't deal the same card twice because we're dealing a standard 52 deck. And does the order matter? In other words, does the order of the hand determine whether or not we dealt them 5 spades? Yeah, no. We don't care about the ordering here. So order doesn't matter, repetition doesn't matter. So what's the formula that we use to count this?
Choose.
Yeah. We're just going to use the standard choose the combinations formula. Right. So what are we how many items are we choosing and what are we choosing from? So remember that the N in this form that represents everything we're selecting from, and the R is the number of items we want to select. So how many spades are in a standard deck of 52 cards? Well, the number of spades, that's just 13. And then we want to select 5 cards. So this is just 13. Choose 5. Any questions with this first part?
You can leave it as choose 13-5.
Yeah, that's fine. I think we'll do what we did the last quiz, where we just said you can leave it in this formula. You could change it to the other formula, because this is just equal to 13 factorial over 5 factorial times 13 minus 5 factorial. And that's one of the formulas on the formula sheet that you have. So you could use that too if you wanted. But you'll have this formula. If you look at the formula sheet that one of the professors sent out earlier this morning, I believe, it gives a list of all the equations that we'll just provide to you. And then you get additionally that extra 2 pages of note sheets of your own. So then if we do B, right, we're supposed to solve problem A if the player is dealt an ace high spade flush. So in other words, we have 5 spades, and one of those is an ace. So how do we end up counting this, right? So does anyone have any ideas first on what would kind of be the technique for this problem?
So like originally there was 5 spaces, but one of them is taken up by the ace. So then
Yeah,
use the 4 positions.
perfect. Yeah, so let's imagine that we deal the ace first. Right, because we have to deal out, we want to count the number of ways we can deal this ace high space flush. So let's imagine that we deal the ace first. Yeah, then we've got how many ways left over? Well, we only have 12 cards left because we took one of them out as the ace, and then we want to select 4 cards out of that because we already dealt one of the cards. And that'll be the number of ways that this can happen. Any questions with that? Awesome. Then let's keep moving ahead. So the next one I think is also a probability problem. Yeah, so what's the probability of getting at least 2 3s on 5 tosses of a fair 6-sided dice? So if we want to look at this probability, right, what's the technique that we're going to use to apply here if we have 5 trials?
A Bernoulli trial.
Yeah, we're going to look at a Bernoulli trial, and we just need to count up basically all the different cases that this can happen. So if we want at least 2 3s, then we want to count either the number of ways we get 2 3s. We could get 3 3s. We could get 4 3s. And we could get 5 3s. Right, and then we just for each of these, we just apply the standard formula from the Bernoulli trial. right? So we've got 5 tosses, and in the first case, we want to choose 2 of them to be 3s. And then there's a 1/6 probability that there are 3, and we want 2 of them. And there's a 5/6 probability for all the others, and we want 3 of those. And then we just continue with the same process. So for 3, we're going to select 3 of them to be 3s. Whoops. And then for 4 3s, we want to select 4 of them to be 3s. Oh, that should be a 2 there. And then for all 5 to be 3s, we want to select all 5. And then there's 1/6 to the 5th probability of that. And then if we want to know the total probability, we can just add up all of these. And then that'll be our total probability of getting at least 2 3s on these 5 tosses. So just applying just the standard Bernoulli trial formula, and then we just have to look at what our cases are. So remember, this is the same technique that we used when we did all of those like ball game problems, where we had different teams and the odds that they would win like a best of series tournament. Right? This is just that same process. So are there any questions here?
Is it possible to solve this problem with the complement rule?
Complement rule. Sure. I mean, we could certainly look at the probability of. So if we want the probability of getting at least 2 3s, then we want to look at the probability of getting at most 2 3s. And then you would do a similar process. So we'd have we could have 0 3s, 1 3. And this would actually be, I guess we just have 2 cases, because this would be the probability of getting less than 2 3s. So yeah, this would work. The probability of getting no 3s, right? If we just work this out really quick, right? We would select out of the 5, we'd select 0 of them to be 3s, and we would just want the probability for the rest. So that'd be 5/6 to the 5th. And then for 1 3, we select 1 of them to be 3s. So that's 1/6 to the 1 times 5/6 to the 4th. And then for the probability here, the final probability would just be 1 minus the sum of these. Yeah, so this ends up being a little bit less work, and you get to the same results. But yeah, that was a really good idea to look at the complement. Often with these counting problems, the complement is a really good thing you should just always check. Like whenever you start a counting problem, that looks like it's starting to be difficult. If you're doing it the standard way, and you're like, wow, this is a really tough counting problem, that's when you should stop yourself, think, hey, what's the complement of this problem? Is the complement easier to solve than just the standard way of counting? Yeah, it's a really good question. Any others here? Awesome. Let's keep going. So we've got this one. I believe this one was actually in one of the previous practice quizzes. Or this was actually in your quiz. This one that they added to the practice final. So we can go over it if you'd like.
Yes, please.
Yes. Okay, sure. Yeah, let's go over it. Okay, so we've got 30 children from the 4th grade, and there's 15 boys and 15 girls. And they're all standing in line. And so we want to, and then we're going to assume that all the ways that they could line up are equally likely. And so then, assuming no two children have the same name, what's the probability that the children appear in line in alphabetical order by name? And then we get this hint. There's only one alphabetical order among all possible lines, right? So the probability that no two children, that they end up in line in alphabetical order, right? For A, like the probability of, let's just call this event X, is we've already got one. There's only one alphabetical ordering. And they want to divide by the total number of possible orderings. Right, because we're looking at the number of elements in our event space divided by the number of elements in the sample space. So what would the number of ways, what are the total number of possible alphabetical orderings among 30 children?
Uh, 30 factorial.
Yeah, it's 30 factorial. And we can also think about that as like, this is, we could apply the permutation formula here, right? Because order matters, right? We're doing them all in line, but we don't allow repetition. So you can't put the same name twice in this list. And that would be the permutation of 30, and that'll be 30 factorial. And then if we look for part B, what's the probability that all the girls precede all the boys? So what are the number of ways that all of the girls could precede all of the boys? Like, how many ways could that happen? So what I count here is, if we imagine kind of dividing our line into two. So we've got a line of all the students, and then we're going to divide it into two. And so these are all the girls, and there's 15 of them here. And then these are all the boys. And so we want to count the number of ways that this can happen. Like, how many different arrangements are there where all 15 of the girls are in front of the 15 boys? And the trick here is the number of ways that we could organize the girls is 15 factorial. And the number of ways that we could organize the boys is 15 factorial. Right, because we could, just using the same logic we did in part A, there's 15 factorial ways to rearrange these, each of these 15 students. So then if we want the probability that this could happen, what would we put on the numerator here?
15 factorial plus 15 factorial.
Okay. Yeah, so someone says, so 15 factorial plus 15 factorial. Maybe I guess we should also ask, would we do times instead? So is this like a plus problem, or is this a times problem?
I know it's times from like the previous exam, but I'm not really sure why.
Yeah, like why is it times? So the thing here is that it is a little bit tricky, especially when you're doing some of these counting problems, to be like, oh, do I add or do I multiply here? And kind of the way I like to think about it is, if you're building up a solution in multiple stages, you're going to multiply. But if you have complete solutions and you're like subdividing the problem like into complete separate solutions, then you would add those. So we want to ask ourselves, is a lineup, the number of ways to line up the girls, is that a complete solution to the lineup of all the children?
Could you repeat your little trick again, please?
Yeah, so the question is whether or not you're going to build your process in stages. So if you are building a solution via, I'll call this kind of like maybe let's call this like incomplete stages, then you multiply. And so why do we multiply here? Well, the reasoning is that if I take the 15 factorial ways to arrange the girls, that's not a complete arrangement. That's one stage, but it's not a full solution, right? A full solution means that I have a way to organize all 30 students. And I don't have that way. So that's why I say I'm building this in like an incomplete stage. The first stage is you organize all the girls. And then the second stage, you would organize all the boys. And once you've done that, you've organized all 30 children. And another way you can kind of think about it is that these are both like independent of each other. The number of ways to arrange, like for each of the arrangements of all the girls at the front of the line, I could use any one of the number of arrangements for the boys in the back of the line for every possible arrangement. So that's why we're multiplying here. And then just like we did in part A, we divide by the same sample space. Our sample space hasn't changed here, so we divide by 30 factorial. So are there any other questions here on this one? Awesome. And then so the last part, so what's the probability that they alternate by gender in line? So the way to think about this one, let's go to another page here. If we want them to alternate in line, so we want like either like a girl, then a boy, then a girl, then a boy, etc. Or we could have like, you could have a boy start. So those are kind of like the two ways we could have one of these arrangements. So either the girls are the first ones in line, first one in line, and then we alternate, or the boys are the first in line, and then they alternate. And then we want to look at what are the number of ways. So how could we arrange the girls and the boys here? And for each gender, again, like we solved in part B, there's 15 factorial ways to arrange the girls in this line and 15 factorial ways to arrange the boys in this line. Right, because they're just all alternating. So if you kind of imagine there's an ordering for all the boys here, and then there's an ordering for all the girls here. And then there's just two possibilities, either the boys start or the girls start. So the probability of this event is 2 times 15 factorial times 15 factorial divided by 30 factorial. Because there are two ways for us to select which one goes first. And then 15 factorial ways to organize the girls then, and then 15 factorial ways that we could organize the boys in line. So any questions here? Awesome. So let's move on to problem 6. So we're basically given a bunch of sets here, and we're looking at like the intersection or the difference or the complement of some set A, and then the empty and the universal set. So let's just go through all of these. So if I take any set and I intersect it with the universal set, what would I get back?
Just
A?
A.
Yeah, just A. Because the universal set contains everything, so the intersection of this is just whatever was an A. And then what about set difference? So take A, set difference A.
The empty set.
Yeah, just the empty set. You kind of imagine like pulling out all the elements of A. What if I take A, set difference with the universal set?
A complement?
So not quite here. And the reason, remember, the universal set contains everything that could be in the set. So we're taking A and we're subtracting out. Basically, you can kind of think of it as like you're subtracting out any possible value because the universal set could be anything.
Oh,
So you'd actually end up with the empty set here. Because remember, A contains everything. The universal set contains everything that'd be an A. So when we take the set difference, you'd be like subtracting those elements out. And you'd end up with the empty set.
If you had universal set minus A, would that be a different answer?
Yes. Yeah. And maybe that's what you're thinking. If I did the universal set minus A, then that would be A complement. Because you're taking everything in the universal set and you're subtracting. You're just taking out all the elements that were in A. So you're just left with everything that wasn't in A or A complement. Yeah, that was a really good question. So what if I take A, set difference with the empty set?
Just A.
Yeah, just A. I didn't take anything out. And what if I take A, set difference with the A complement?
Just A.
Yeah, just A. And then what if I take A complement complement?
A.
Yeah, that's just A again. Any questions with these? Just a little it was a little refresher of some of the set properties we deal with. So then let's go to part B. So suppose A and B are sets. And then we brought the power set of A. And we want to use a direct proof. I want to show that the following holds. So we assume if the power set of A is a subset of the power set of B, then A is a subset of B. So how do we start? What's the first thing we're doing? We got a direct proof problem, right? What's the first thing in this case that we should write down? Like even before we start to do any work, just kind of starting off our problem. What would we like assume to be true at the start of our proof?
if X is in A, then it's also in B.
So not quite. That's kind of like what we're supposed to like show, right? To show that A is a subset of B, we want to show that every element of X is an element of B. But what we want to assume first is we want to assume our hypothesis is true. The hypothesis here is if the power set of A is a subset of the power set of B. So we just assume that this is true. The power set of A is a subset of the power set of B. And then now, based on this assumption, right, we just need to show that A is a subset of B. And like you were saying, a really good argument here. So to show that A is a subset of B, we need to show that every element of A is an element of B. So let's look at an element. So let's let like little a be an element of our set big A. And then I'll just put like in parentheses. And then we want to show that X is an element of B. And if we can show at the end that X is an element of B, then we've shown that these two things are subsets of each other. Or that A is a subset of B, excuse me. So if we know A is in this, little a is in this big set A, what do we know? What's an element we now know is in the power set of A?
A.
The set containing A, yeah. Because if A is an element of A, then this means that the set just containing A has to be in the power set of A, right? Because the power set is just the set of all subsets. So if A is an element, then the set containing A is a subset of A. So that's got to be in the power set. So I know it's in the power set of A. Is there anything else I know about this set, the set containing little a? Do you know it's in anything else? See, like from our hypothesis, if we know that the set containing little a is an element of the power set, and we know that the power set of A is a subset of the power set of B, does that tell us anything about the set containing little a and the power set of B?
A is in the element of the power set of B.
Yeah, the set containing A is an element of the power set of B because they're subsets of each other. The power set of A is a subset of the power set of B, so every element in the power set of A is an element of the power set of B. So that's just sense. So now I know that the set containing A is an element of the power set. Does this tell me anything about A in relation to just the set B? So what does it mean that little a, the set containing little a is in the power set? Right, it means that the set containing A is a subset of B. Right, so we can write that out. So then little a is a subset of B, and that's just by the definition of the power set. And what does this tell us? If little a is a subset of B, what can we conclude?
Then that means the element of A is in B, so then A is a subset of B.
Yeah. Oops, I had X. Yeah. So then, yeah, A is an element of B because it's the set containing A is a subset of B. So we let A be some element of A. We showed it was an element of B. So thus, A is a subset of B. So this is like the typical way that we would prove subset. Right, you start out with some element here, and you just show it has to be an element of the other. Now this is like the typical form we'd follow if on the final you had to prove some set was a subset of another. You'd follow this similar approach with this kind of element-wise technique. Any questions on this one? Okay, let's move on. Okay, so problem 7. So this is on relations. So we're looking at some relation R over the integers. And R is this set. And so first we're asked, is R an equivalence relation on A? So is R symmetric? Is it reflexive? And is it transitive? So what do you think about reflexive? Is R a reflexive relation? Over the set A?
Yes.
Okay, so you said yes, someone else has said no.
because
Any
it's
other ideas?
because it doesn't have 2.
Yeah. So yeah, in this case, it's no, it's not reflexive. 2, 2 is not an element of R. So it's not reflexive. Because reflexive means that every element in A would have to be related through R. So you need 1, 1, 2, 2, 3, 3. And that doesn't happen. So in this case, we can just conclude right there, know that this is not an equivalence relation. But let's go through the others as well, just so we get a little bit of practice. So is R a symmetric relation? So in other words, if x comma y is in R, does that mean y comma x is in R? What do we think?
No, because there's no element with 2 in R.
Okay, so someone says no. Anyone else have any ideas, or do we all kind of agree with the no?
I'd say yes, because every element that is in R has its opposite or whatever.
Yeah, and that's the reason, and that's why we have to be careful sometimes when we're looking at stuff that's symmetric. This is symmetric. Yes, this is symmetric, and that's the perfect reasoning. Symmetric doesn't mean that every element, right? If we look at the definition of symmetric, symmetric says basically that if xy is an element of R, then y comma x is an element of R. And it starts with this assumption that x comma y first needs to be an element of the relation. And then only when that happens do we care if it's symmetric. So here, right, 1, 3 is in the relation, and 3, 1 is in the relation. And 1, 1's in the relation. If you flip it, 1, 1's also still in the relation. Same with 3, 3. So this is why it's symmetric, because we're just caring about, you just have to look at what stuff is in R when you're looking at symmetric. And if like you can flip both of them, basically swap both of these, and if that is still in the relation. And then what about transitive? Do we think this is a transitive relation?
Yes.
Yeah, it is. It is transitive. And why? Well, let's look at it this way. One way we can check is if you just kind of go through it and look at all of the possible pairs. So like 1's related to 1, and 1's related to 3, and we have 1 related to 3 because that's just this pair. 1's related to 3, and 3's related to 1, and then we have 1's related to 1, right? Because for transitive, we're looking at if A is related to B and B is related to C, you have to have A related to C. And we have the opposite way. Like 3's related to 1, 1's related to 3, and we have 3's related to 3. So yes, it is indeed transitive. Oops. Any questions there that we didn't answer? Awesome. So then let's look at B. So now we're changing the relation we're over. We're changing the set we're over. So now is R an equivalence relation over the set containing just 1, 3? So in other words, now is it reflexive symmetric, and transitive. So now, do we think that this is this reflexive or not if we change the set it's over?
Yes.
Yeah, it is reflexive because now we're just looking over the set 1, 3. 1's related to 1 and 3's related to 3, so it's reflexive. Is it still symmetric?
Yeah.
Yeah, and then it's still transitive for the same reason. So in this case, if we've changed the set it's over, in this case, yes, R is an equivalence relation. Any questions here? Awesome. So let's move on to the next part. Let me just rewrite it on the next slide because we ran out of space. So let's let A be a set of non-zero integers. And let this be the relation on A cross A. That is, R is a subset of A cross A. And then we define this operator, this kind of squiggle sign, as follows. So AB is related to CD whenever A times D is equal to BC for AB and CD in A cross A. And then we want to prove that R is an equivalence relation. So we've got an equivalence relation proof. So just like you're going through, in this case, we have to prove it. So we have 3 parts we need to prove. So first we need to prove that R is symmetric. In other words, we need to prove that for all X in A, that X comma X is in the relation R.
Isn't that the rule for reflexive?
No, this, yeah, it is. I meant to write down reflexive. Yeah. Good catch. Yeah, I wrote down the rule for reflexive. I don't know why. Set symmetric. Yeah. I just generally like to start with reflexive because I think it's the easier one of the 3 properties to prove. So if we're going to start with reflexive, how could we start to show that this is reflexive? I guess what we're really looking at here is, because we're doing it over the cross product, I guess I could make this a little bit more formal. That we should be looking at for all X comma Y in A. that we want to see that the xy is an element of the relation R, because we're over the cross product, where each of these are. Yeah. So for
Wouldn't-
this, yeah, go ahead.
Wouldn't the definition of cross product automatically mean it's reflexive? Because like each term is always going to be paired with itself at least once.
So yeah, cross product will, but we're defining this relation over the cross product, and we're defining this relation so that AB is related to CD whenever this happens, right? Whenever A times D is equal to B times C. So what we're looking at then is in this particular relation, like for this to be reflexive, we would need AB to be like related to itself. We haven't dealt a lot with like looking at relations with operators. We just kind of like, in a lot of the problems we've looked at, we've defined them, and we've just specifically stated what the relation is or how the set is constructed. But this is just a different way to do that, where we're saying that AB with the squiggly symbol C comma D just means that these two items are related. So for reflexive, we need to show is A comma B, is that related to itself? So in other words, I guess I should have rephrased, yeah. This should really be like, yeah, for all x comma y. Yeah, that's fine. So how do we show this? How do we show that AB is related to itself? Well, we need to just check the definition. So this is related if A times D is equal to B times C. So we take A times this, and these two times each other. So is A times B equal to B times A? Because that's the operation that we're looking on to determine whether or not this is in the relation. So does this happen? And is this always true? Yes, it is. Right, A times B is equal to B times A because we have the commutative property for multiplication. So AB is in the relation. Or in other words, yes, indeed, AB, because we've kind of defined it with this operator, is related to AB. And then for symmetric, right, we would say assume that AB is related to CD, and we would like want to show that CD is related to AB. So what does it mean for the tuple AB to be related to the tuple CD? So if this, oh yeah, go ahead.
AD equals BC.
Then AD equals BC. For us to show this, in order to conclude this, right, we need to show that like C times B is equal to D times A. So, and we can do that. We can swap these using commutative. D times A is also equal to C times B, just using commutativity of multiplication. And this tells us thus, if DA is equal to CB, that means that CB or CD is related to AB. And then for transitive, we'd assume that AB is related to CD. And then CD is related to EF. And then, right, we want to show that AB is related to EF. So if AB is related to CD, then that means that AD is equal to BC and CF is equal to DE. Okay. And at the end, we want to show somehow, in order for this to happen, we want A times F to equal B times E. So we want AF to equal BE. And we want to figure out how we can get that from these two equations. Anyone have any ideas for how we could get these two, how we could end up with that equation from these two?
Can we substitute it all?
Can't substitute. Well, we could substitute certainly, but it wouldn't. I don't think it would end up getting us too far. So, okay, so the trick here is, right, what are the common letters here? So there's a D here, and then D here, a C here, and a C here. And we don't have any D's or C's in this equation. AF is equal to B times E. So the idea here is by somehow we want to like cancel those out from each other. And what we could do is if we notice that like both of these are on the C is, there's a C and a D on the left side and a C and D on the right side, is we could like multiply these two statements together. So then we would have A times D times CF is equal to BCDE. And now we've got this like C and D here that we could cancel out. But how do we know that we can cancel out, that we can basically divide by C and divide by D? Is there something in the problem that tells us that that's allowed? Or in other words, that like these are non-zero? So yeah, so in the problem we said A was a set of non-zero integers. So we know that C or D are not zero. So we can divide through and we'll end up with the equation AF is equal to BE. Thus, AB is related to EF. Any questions here? This is a little bit of a confusing problem. Partly just because we haven't dealt a lot with relations, just defining like kind of new operators for them, or over like the cross product, for example. But all the same properties kind of still hold when we're proving like reflexivity, symmetry, and transitivity.
I'm a little confused about the step where you set A, D, C, F to B, C, D, E.
Sure, yeah. What are you confused about here? Like why we multiply them, or why this works out?
Kind of just how you did it. I think I might have missed like the thought process.
Okay, yeah. So the thought process. So this is like this is a little tricky spot to come up with. To figure out that you have to like multiply these two things. But the thought was, okay, so if we look at both of these two equations here, I guess let me get a new page here. So what do we have? AD equals BF. And CF equals DE. So if we look at both these equations, right, they both share, so there's a D in both. Oh, BC. And there's a C in both. But the final equation we wanted is we want an equation that looks like this. We want something that's A times F equals B times E, right? Yeah. So this is like the equation we're looking for. And we want to find it from using these. Well, what we notice is, right, both of these, so one side has a D and one has a C, but there's no C's or D's here. So that gave us the idea that maybe there's some way we can like combine these equations and cancel terms somehow. And the idea is that, well, we could multiply both sides, and then we'd have a DC on one side and a C times D on the other. So then once we get here, right, the idea is to multiply. Then we have a C and a D on one side, a C and a D on the other. And because these are non-zero integers, as was given in the problem, then we can cancel and end up with the formula we want. That was kind of the thought process. It's a little bit tricky to come up with that. So got to be a little bit clever.
And you can multiply them onto each side because they're equal to each other.
Yeah, only because they're equal. Because AD is equal to BC and CF is equal to D.
Got it. Thank you.
So you're just multiplying both sides by the same value. Awesome. Any other questions on this? Awesome. So let's move on to 8. So here we've got an induction problem. And so we're going to show that the sum from I equals 1 to n of I times I factorial is n plus 1 factorial minus 1 for all n that are positive integer greater than 1. So we've got an induction problem. So we just follow basically the steps that we've always done for induction. Right, so we've got the problem statement. And we have this hint that's basically tells us the problem statement is we're going to define P of n as this thing. So we got the problem statement. Now we've got to show the base case. In this case, we're proving it for n being a positive integer greater than or equal to 1. So the smallest we could have for n is 1. So our base case is n is equal to 1. And then, so base case, so we want to show that p of 1, show p of 1. So let's work out both sides. So if we work out, so the sum from I equals 1 to 1 of I times I factorial, that's just 1 times 1 factorial, which is 1. And then if we use the other formula, 1 plus 1 factorial, minus 1 is 2 factorial minus 1. 2 factorial is just 2. 2 minus 1 is 1. So these are the same. So both are equal. So we've proven the base case. All right, we should both gave us 1. So now we need to write the induction hypothesis. And we can just do this by, there's lots of different, like you could assume that P of n is true, show P of n plus 1. Let's just assume that that this formula holds for n minus 1. Or in other words, assume that P of n is equal to, P of n minus 1 is equal to this formula. Right, and then now we want to prove it's true. We just assumed it's true for the previous n minus 1, and now we want to use induction step. And then here we want to use, basically, we want to use P of n minus 1 to prove that P of n is true. That P of n is equal to this. So let's start with what we have for P of n. So we've got the sum from I equals 1 to n of I times I factorial I guess let me simplify some notation here. Otherwise, this is going to get a little bit messy. We'll just use the P of n because we're using P of n to kind of represent this complicated summation. That way I don't have to keep writing it. I could have written the other way. It'll just, this will go, I won't have as much to write. And it'll look hopefully a little bit smoother for you all. So if we have P of n, right, is the summation from I equals 1 to n, we can look at as this is, it's really the P of n minus 1. It's really the sum from I equals 1 to n minus 1 of I times I factorial, and then plus this little extra bit. So plus n times n factorial. the nth term. Right, we did this a lot, if you remember back in induction, when we have these summations, is you kind of take out the last term, and then you can use the induction hypothesis on this previous summation. So P of n is equal to P of n minus 1 plus n times n factorial. So what would our next step be? What does our induction hypothesis tell us, right? The induction hypothesis tells us that P of n minus 1 is equal to n minus 1 plus 1 factorial minus 1. And if you simplify that, that's just n factorial minus 1. And this is just by the induction hypothesis. Right, tells us whatever P of n minus 1 was. And then now we just have to figure out how, some way to combine these two statements. So we can end up with n plus 1 factorial minus 1. So what we can do here is we've got this common n factorial term. So we can factor that out here, and we'll end up with n factorial times 1 plus n minus 1 from that leftover minus 1. And let me rewrite it a little bit. That would just be n plus 1. And what's n factorial times n plus 1? How could we write that a little bit differently? So that's in the form that we want, because we're looking for this formula. Well, n factorial times n plus 1 is that's just n plus 1 factorial minus 1. And that's exactly what we wanted.
Can you explain how you got to the second to last step?
This one?
Yeah.
Okay, yeah, sure. So so we can rewrite this. This is just n times n factorial plus n factorial minus 1. So I just did some term rearranging. And then you just factor out this n factorial. And if we factor out the n factorial, that'll be n plus 1 minus 1. And then we can just use that is just n plus 1 factorial minus 1. Does that help?
Yeah.
Okay, awesome. So are there any questions here for this? And then we could write some concluding statement. Like this, the sum from I equals 1 to n of I times I factorial is equal to n plus 1 factorial minus 1. But any questions on induction? Awesome. Certainly, make sure you review it. Certainly an important thing. You're likely going to see an induction problem on the final exam.
I have a question.
Sure.
So this problem has an x as the multiplication sign, and I kind of thought that meant cross product. So, is there any way a cross product induction problem will show up? Because I might get those mixed up.
You certainly could do an induction proof. I mean, induction is just a proof technique. I believe problem 12 of the final is a graph problem, but you use induction to prove it. So you can use induction, and certainly there could be something on sets that you could use induction for. But the difference is it wouldn't be within a summation. So like, unfortunately in math, we like overload a lot of operators, I guess, like that this both represents times as well as cross product. So you just have to be careful and look at like the context that it's in to determine what it means. So in other words, like you have to be like a really good like compiler, I guess, for these math symbols to look at like the context that they're in to determine what they mean. So since we're in a summation here and we're just looking at integer values, these I is not a set, so it doesn't make sense to look at like the cross product.
Oh, okay. Thank you.
So you just have to be, you just have to be aware of like the context of the problem.
How did you get n factorial times n plus 1 minus 1 equals n plus 1 factorial minus 1?
Oh, sure, yeah. So let me get a new page. So if you remember, like, let's just look at it from like the other direction. So if we look at n plus 1 factorial, right, n plus 1 factorial, that's just n plus 1 times n times then minus 1 times like n minus 2, right? Until you get down to like 3 times 2 times 1. It's just the definition of the factorial, right? It's the product of every the integer itself and then every preceding integer down to 1. But if you look at this here, right, n factorial is just n times n minus 1 times n minus 2 times. So this here is n factorial. And that's just n plus 1 times n factorial. So we just kind of did this process in reverse. And then I just said, well, n plus 1 factorial, you could rewrite it like this, and that would be the same as n plus 1. Factorial. Does this help?
Yeah, thank you.
Okay, yeah, no problem. So any others on induction? Okay, awesome. So we have about like 20 minutes left. Do we still just want to keep going with the rest of the practice final? Or are there any like pressing questions you have that haven't yet been addressed that we could spend any time on?
Can we do graph examples, please?
Sure. Do you want the ones just on the practice final?
Sure.
Okay. Actually, okay. Let's see. So we can go through 11 and 12. They're a little bit more challenging, these ones. But yeah, let's see if we can go through them. And then Zoe also did some extra graph problems as well for her morning review session. And she started with a bunch of the practice problems. So that would also be a review you could take a look at as well if you wanted to see a couple more problems, because she started with the practice problems and then went to the practice quiz or practice final. So that one would have some more problems if you want to see as well. But here, so we're basically defining a plane graph is a planar embedding of a planar graph, right? And a planar graph is just a way to like draw a graph on a plane so that no edges cross each other. So as long as there's a way you can draw that, we call that a planar graph. So something like, for example, like this, like if you had a graph like this, you know, this is a planar graph. but but this graph here, so this is a planar graph. It can be drawn on a plane, no edges crossed. This is not planar. There is no way to draw this graph on a plane without two edges crossing over each other. So that's just what we mean by planar. And then we're going to prove that if G is a plane graph with more than two vertices, then G has a vertex of degree at most 5. So what we're saying is that, like, there is at least one vertex that has degree of at most 5. So it's not true that all vertexes have a degree 6 or more, is another way to phrase what this is. And then if this was on the final, we'd probably tell you to hint to use contradiction. So if we're going to prove this, because on the final, we'll give you hints to tell you like what proof technique you should use. So if we're going to use contradiction to prove this, we would just use basically assume that let's let G be a plane graph. And then we're going to assume, I guess let's make sure, like, to the contrary, because we're doing a contradiction proof, that every vertex in G has degree of at least 6. Right, just using contradiction, we just negate the conclusion from our proof statement. So we're going to assume that we've got this plane graph and every vertex has degree at least 6. And now we want to find some contradiction. Now the trick here is we want to utilize what's known as Euler's formula. Right, and if you recall, what Euler's formula said is if we have a planar graph, then the vertices plus the faces, the number of vertices plus the number of faces is equal to the number of edges plus 2. So where V is vertices, F is faces, and E is edges. And we could also rewrite this by looking at the number of edges, and this would tell us that edges is equal to vertices plus faces minus 2, which is less than the vertices plus the faces. So Euler's formula tells us that this is always true of a plane graph. The number of edges is less than the number of vertices plus the number of faces of your graph. And we want to utilize this statement here in order to prove this problem. So what we're going to do is we're going to look at ways to count the number of vertices and to count the number of faces of this graph and show that it's larger than the number of edges, that the sum of the vertices plus the sum of the faces is indeed larger than the number of edges. And that's what we're going to work towards. And that'll be the contradiction. So let's look at how we could count the number, the degrees of the number of vertices. So if every vertex has degrees of at least 6, then we can kind of like label these vertices as follows. So let's let V6 be the number of vertices with degree 6, and V7 with 7, et cetera, et cetera, et cetera. So the number of vertices is the number of vertices of degree 6 plus the number of vertices of degree 7, right? And so on and so on. Because every vertex in our graph has degree at least 6. So we can start from here. And then what does that tell us about the number of edges? Well, if you recall, we also have said, let me write like a little aside here. That the sum of the degrees of each vertex in a graph is equal to 2 times the number of edges in the graph. So this is also a formula that we know. So then just by that, 2 times the number of edges is equal to, we've got vertices of degree 6. So there's 6 times V6 plus 7 times V7 plus 8 times V8. Right, because 6 is the number of degrees, is the degree, and there's this many vertices of this degree. So this over here, this represents the sum of the degrees. In the graph. And that's just from a formula that we were given, that 2 times the number of edges is equal to the sum of the degrees. That'd be a formula I would definitely have on your formula sheet, as well as like Euler's formula. There's a lot of notation and like definitions and graphs. So I'd make sure you add that to the formula sheet. So then if we continue, and we look at what happens if we take like, let's say 2e minus 6v, and the reason why we're doing this right now is a little bit like if this was around the final, we'd certainly need to give you hints, a few more hints through this. But if we look at this, we would cross out the number of v6s, because 6 times v would be 6 times 6 plus 6. You just multiply everything by 6, and if you subtract these two, we'll get v7 plus 2v8, and etc. And the important part here is that these values are all greater than or equal to 0 to right now. So 2 times the number of edges minus 6 times the number of vertices is greater than or equal to 0. Now what we're going to do is we're going to look at how to count the number of faces. And then we're going to combine these two formulas and use Euler's formula. This v plus f is equal to e plus 2 to conclude for this problem. So if we look at the number of faces, right, and if we do this a similar thing, so f3 is the number of faces with 3 sides. We can't have a face with 2 sides on a planar graph, right? We have to have at least something that looks like this. F4 with 4 sides. Then the number of faces is F3, number of faces with 3 sides plus 4 sides plus 5 sides, etc. And then we also know something similar to faces, or similar to what we did with 2 times the number of edges, is we also know that 2 times the number of edges is equal to the number of sides, the sum of the number of sides of the faces. So in other words, just like we did before, we'd have like 3 times f3 plus 4 times f4 plus 5 times f5. Right, and this is just the sum of the number of faces, or the number of sides for each face.
Can you explain again why you started 3 for the faces?
Because we can't have a face with 2 sides on a planar graph, right? Because we've just got like straight lines here. So this doesn't create a closing. Like it doesn't create like a polygon. So we need at least 3 sides in order to create this closed space that we call a face.
Doesn't that make 2 faces though?
Yeah. So there are 2 faces with 3 sides here. There's the internal one, and then there's the one outside. So that would be included in the number of faces of 3. But yeah, because there's 2 faces in this. Yeah. And we're just doing that here because it's a planar graph. And that because it's a planar graph, then we know that each face has to have at least 3 sides.
So the definition of planar graph demands that it has at least 3 sides? So why was that triangle not considered a planar graph then if it had 2 faces?
Oh, it is a planar graph, but every face in this graph has 3 sides.
Oh, so we're not counting the number of faces in this, we're counting the number of
No,
sides.
we're counting, yeah.
I see.
Yeah, like here, where 2 times the number of edges is the sum of the number of sides.
I see now.
And then if we use this, and we use a similar technique as we did before, so we'll multiply these by 3, then 2e minus 3f is equal to f4 plus 2f5, and this is greater than or equal to 0. So 2e minus 3f is greater than or equal to 0. And what we had before is we had 2e minus 6v is greater than or equal to 0. So what we can do is if we take 2e minus 6v and we add 2 times 2e minus 3f, what we're going to end up with is everything is going to have a 6 in front of it, because this would be 2e, or this will be 2e minus 6v plus 4e minus 6f. That'll be 6 times e minus f minus v. And what do we know? We knew that this was greater than or equal to 0. We knew that this was greater than or equal to 0. This tells us that this is greater than or equal to 0. In other words, then e minus f minus v is greater than or equal to 0. And that implies that e is greater than or equal to f plus v. And this is the contradiction. Why? Well, we said from Euler's formula, this vertices plus faces is edges plus 2 for plane graphs, that e must be strictly less than the number of vertices plus the number of faces. But we found, why did that? How did I select that? But we found that the number of edges was greater than or equal to the number of vertices plus faces. So that's a contradiction. So thus, contradiction. So G has a vertex of degree, at most 5. So that problem's a little bit complicated, but hopefully some of the ideas about looking at edges, vertices, and faces, and counting sides and degrees made some sense. Are there any questions about that one? I know it's difficult.
I have a question.
Yeah.
Are sides and edges the same thing?
Yes. Like the sides of a face are defined by the edges in your graph.
Okay, thank you.
Any other questions? Awesome. So we have about like 2 or 3 minutes left. Not enough time to go through a full problem, but are there any last minute questions that you have? Again, you can check out Zoe's morning review session as well. She went through all of the practice problems that were picked out. So those problems you wouldn't have seen before. And then she also went through, I know problem 12 that we didn't get to. And maybe 9 or 10 as well. I don't remember. So you can also check those out if you have more questions. And there's office hours tomorrow and on Wednesday if you have any last minute questions as well. But any questions I can answer here?
So should we prepare our sheet with all the different like graph theorems and stuff we use to prove?
Yeah, I would definitely add some of those to your formula sheet, certainly. Yeah, like Euler's formula, like that the sum of the degrees is 2 times the number of edges. There's several other formulas on graphs as well. There's a lot of material on graphs, especially like some of like the definitions and stuff. And if you're not as comfortable with those, I would definitely write them down. Because for the rest of the sections, if you look at the formula cheat sheet that one of the professors posted, has a lot of the other material on it, but nothing on graphs. So I'd make sure you add a decent number of stuff on graphs for your problem, for your formula sheet. And then remember that this time you get 2 pages rather than just the 1 page like we had for the previous quizzes. Any other questions?
I have a question.
Sure.
So on the final exam, will the type of questions be like an even mixture of all the topics we learn, or will a certain topic show up more than others?
I don't know quite how to answer that. We will certainly have like a question from all the major sections. Certainly. Will one show up more than others? It's hard to say. Like, I mean, you'll certainly have several proofs. So like you could say, does that mean that like section 2 is more weighted when we were learning about proofs? No, not necessarily, because you could have like a set proof in a proof on graphs, for example. But I believe we will also tell you, once we've finalized the final, we'll tell you the number of questions. And I think we'll tell you how many are from like each chapter. Certainly there will be at least 1 from every chapter of the book.
Okay.
Maybe except like the first chapter, because that's kind of basic. Does that help? It's hard to say like what will be more important,
Yeah, this
but it'll cover every topic.
okay. Thank you.
Awesome. So that's all the time we have. If you have any other questions, post them on Piazza or stop by office hours on tomorrow or Wednesday. And good luck on all your final exams.